Hi everyone, this is Mrs. G, and today we're going to talk about linear approximations and differentials. All right, I have a quick warm-up for you, so please pause the video and give it a try. All right, so here, this should be a pretty quick and easy warm-up for us, right? We're just making a tangent line equation. So this should be something that we can do like very, very quickly and easily at this point. Typically, I would say leaving it in point-slope form is fine, but today you'll notice that I wrote it in slope-intercept form because we're actually going to be using this function today. So today we're going to be finding linearization functions, which is really just a fancy way of naming a tangent line equation. Okay, so let's look at the graphs from our warm-up. So this is actually a graph of the quadratic from the warm-up, and there's that tangent line. So you can see it's intersecting at 1, 1. So now let's imagine a scenario where I asked you to find maybe f of 1.1. And let's say you didn't have a calculator, so you were plugging 1.1 into that quadratic function from the warm-up. So that wouldn't be that hard to do, but you can imagine that it would be a lot nicer to plug it into a linear equation. So if you look at these zoomed in graphs, so I'm getting closer to that point of intersection, and then as I zoom in even more and even more, you can see that the two equations are almost identical. So when we're working really close to x equals 1, our tangent line is going to be a really good approximation for our original function. So then we're essentially saying, well, instead of plugging 1.1 into a quadratic and having to simplify that by hand, we could actually plug it into the linear function, which would just be an easier function for us to use, and that will give us an approximation that's very close to the actual value. Now, that being said, right, we only want to use a linearization function, aka tangent line, when we're close to that point of intersection. So if I'm trying to approximate f of 1.1 or like 1.01, it would work really well. But I wouldn't use it to approximate f of 0 or f of 2. That's going to be much farther away. So I'd say typically maybe 0.1 above or below the x value, it will be pretty good. So let's test out that theory. So here we have the original function from our warm-up, and then 3x minus 2 was that tangent line equation. So now I'm just calling it L of x, which stands for a linearization function. So let's say I asked you to evaluate f of all of these values. Notice these are values that are really close to x equals 1. So take a moment and let's plug those in with our calculator. Plug these values into f and to L. Now, when you do that, you'll see that the values are actually really close. Now, when we're maybe at 0.8 or 1.2, they're not quite as close. It's not super far off, but it's not a great approximation. But when we're maybe 0.1 above or below, it's a pretty good approximation. So again, this is showing that our tangent line gives us a really good approximation for our original function, maybe 0.1 or 0.2 above or below the x value of the point of intersection. Now, one thing you should notice is that all of our approximated values are slightly less than the exact values. Now, the reason why that's happening, if you think about it graphically, here's our quadratic, here's our linearization. This tangent line is, if you have a graph like this that's concave up, the linearization equation is always going to kind of sit right underneath. So all of the values will be a bit of a underestimation. But let's say you had a scenario where you had like a downward facing parabola, like something like this. If you had a graph like this, all of our tangent lines would sit above, which means our linearization would be a little bit of an overestimate each time. All right, so now we're going to use this linearization function in a little more practical way. So let's imagine I wanted you to give me a rational approximation, so a fraction that approximates the square root of 4.1, okay, which again, a decimal within a square root, it's not a super nice thing to work with. So let's say I had the function square root of x plus 4. Now here, I'm going to make the tangent line equation, aka the linearization, at x equals 0. The reason why I'm doing it at x equals 0 is because, well, when x is 0, I have the square root of 4, which is really close to the square root of 4.1. And in fact, it's 0.1 below it, so it's close enough where the linearization would provide a good estimate. But square root of 4 is a lot nicer to work with than square root of 4.1. So this is why I'm picking to do it at x equals at x equals 0. So let's do the tangent line at x equals 0. So first thing I need to know is f of 0, and if I plug that into the original function, I get 2. And then I need to know the slope of my function, so I'm going to find f prime, so I can find f prime of 0. So f prime of 0 is 1 over 2 square root of 0 plus 4. So it's 1/4, which is the slope of my linearization function. And here I specifically have a y-intercept. So I'm going to go straight to slope-intercept form. Okay, here's my linearization function. And now if I want to use this to estimate 4.1, I need to be strategic about what I plug in. Here, the inside of my radical is x plus 4. So if I want x plus 4 to become 4.1, that means I need to plug in 0.1, or I'm going to say 1/10, into my linearization function. So I'm not plugging in 4.1. There's already a 4 inside my radical. It's 4 plus x. So that means if x is 1/10, then that gives me an approximation for a square root of 4.1. And because I'm working with a linear function, it's a lot easier to plug in. So we'll do L of 1/10, so 1/40 plus 80 over 40. So we have 81 over 40. So this would be a fraction that approximates that value. So just to see how close we are, let's find the decimal approximation of this. So if you do 81 over 40 in your calculator, you get 2.025. And then if you do square root of 4.1 in your calculator, let's see what that is, you get 2.0248 ... So if you compare the two, this is actually a really good approximation for the square root of 4.1. And here we have a rational expression that we're working with, so it'd be a little bit easier for us to work with, especially if we didn't have a calculator. Now, you do notice, or you should notice, that if you compare the approximation and the exact value, the approximation is a little bit of an overestimate. The reason for that, well, let's think about it graphically. The original function, it's a square root function shifted to the left 4. So it looks something like this. So, and we did the tangent line equation, aka the linearization function, at x equals 0. So because we have that concave down graph, the tangent line is always going to sit above, which is why our approximation is slightly higher than our exact value. All right, let's try one more together. So here we have a function, x plus 3 quantity cubed. We're seeing if we can use a linearization function to create an estimate for what 2.03 cubed would be. Again, in this context, we're not using the linearization to estimate f of 2.03. We're actually using it to estimate this value, kind of like in the last example. So first, we are going to need to make a tangent line equation, but we have to figure out where. So if I'm trying to estimate 2.03, I know that if I can turn this into a 2, that will give us a pretty good estimation, and it's going to be a nice, easy number to work with. So if I'd like this to be 2, we're going to do it at x equals 1. So again, we're trying to turn this into a nice number that's very close to 2.03. So if I have x plus 1 and x is 1, that gives me a 2. So let's do the tangent line equation there. So first I need f of 1. So it gives me 2 cubed, which is 8. And then I need the slope, so I need f prime of x first. And then I can find f prime of 1. So we have 3 times 4, which is 12. So we have y minus 8, 12 times x minus 1. And let's call it L of x, and let's isolate y. Let's write it explicitly so we can use it. Okay. So here we have our linearization equation, But now we need to figure out what to plug in. So again, we're trying to estimate the value of 2.03. So here, if I have x plus 1 and I want it to be 2.03, that means that I'm plugging in 1.03 to my linearization function. But we'll keep it in fractional form, so we have a nice exact value to work with. And since we're plugging that into a rational function, it's actually pretty nice to work through. So let's simplify. So we have 3 times 103 over 25 minus 4. So 309 over 25 minus 100 over 25 gives us 209 over 25. So that would be a rational approximation of 2.03 squared. But let's see what 209 over 25 is. So this gives us approximately 8.36. And if I actually do 2.03 cubed, we get 8.365427. So if you compare the two, extremely close. Now, I guess this is a bit of an underestimate. It's a slight underestimate. So again, if you think about what's happening graphically, I have a cubic function that's been shifted to the left 1. So it looks something like this. And remember, we made the linearization function at x equals 1. So it's right here, give or take. So it's at a point when our graph is concave up, so the tangent line is always going to sit underneath, which is why our approximation is slightly lower than the exact value. Again, this is just kind of a more practical application of a linearization function or doing a linear approximation. All right, that is all for today's lesson. Thank you so much for watching.